Okay. So, yesterday we got into it with character tables. We saw how character tables are an assembly of the characters along the diagonal matrix representation, symmetry operation. And then the information along that diagonal is really kind of the most useful stuff. And you can capture all of the symmetry or the operations simply by doing that. And we also talked about rules. You know, these groups, the point groups or the symmetry groups and their associated character tables are complete collections of the symmetry information problem. And there's a bunch of rules that you can use to figure out all of the orthogonal reducible representations that are needed to describe that symmetry. So if you have a big matrix that describes an operation, there's all this stuff along the diagonal, and block diagonalized form, each one of those many matrices that you get along that diagonal ends up making up the irreducible representation. All right, so a couple of rules, right? The character under E is the dimension of the irreducible representation. So if you have two things that are degenerate or three things that are degenerate, the character under E is going to be 2 or it's going to be 3. In a shape like octahedral, where you can't tell the difference between X, Y, and Z, they're indistinguishable, there's nothing unique about X, Y, and Z. All three transform together, and the character under E is going to be a 3. In a symmetry where the X and Y are indistinguishable, but the Z is different, now the X and Y will transform together, and they will be within an irreducible representation that has a degeneracy of 2, or 2 under the E operation. How many of you think, oh, that sounds very familiar? Yeah, I remember that. So. Unique directions, important things to remember when distinguishing between shapes and thinking about character tables. If X and Y are not distinct, they will transform together. Okay, you gotta know that. All right, the order of the group, the number of operations, and it's equal to the sum of the squares of the characters under E. Remember, 2 irreducibles must be orthogonal to each other. So you multiply them by one another and add them up. You're going to get 0 at the end. And also the sum of the squares of the characters in any one group must add up to the order of the group also. All right, so if you know those rules, you can figure out how to make a complete character table. We did that with C3D. We figured out the missing irreducible representation, right? And then we started talking about Mulliken symbols, right? So triply degenerate under E, that gives you a T. Doubly degenerate gives you an E. Singly degenerate can be A or B. What differentiates that, A or B? Well, go to the next most important symmetry operation. That's the principal rotation. If the sign goes from plus to minus on applying the principal rotation, or if the character under the principal rotation is +1, then that group is an A. If the character under the principal rotation is -1, that group is a B. There are also 1s and 2s. Those refer to perpendicular C2s. There are also primes and double primes, which we haven't done yet. Yeah, 1s and 2s can be perpendicular C2s, or if there's no perpendicular C2s, which you won't have if you're in a C and B group, then the 1s and 2s can be used to denote character under sigma b. All right. I'm going to just finish those quickly here. So the fourth one is primes and double primes. This tells you about what happens under sigma h. That means symmetric or anti-symmetric. Symmetric means a 1 is the character, anti-symmetric means a -1 is the character. You have to be a little bit careful because some of these guys don't use primes and double primes if there is an inversion center. Okay. Conversion centers get a special symbol. G and U. G and U refer to Gerada and Ungerada, which I think is German, but I'm not sure, or symmetric and anti-symmetric with respect to inversion. Okay. So G is symmetric with U. Anti-symmetric. Okay, so it's really helpful if you can sort of know these rules and be able to kind of guess what's happening or refer to the character, the irreducible representation by them, and to know what that implies about the characteristics of each irreducible. So let's take a look at an example here. C2H. Deceptively simple C2H. All right, so C2H has a couple of groups. It's got an AG, BG, AU, and a BU. Pretty neat and tidy, right? This is going to be symmetric with respect to the principal rotation, anti-symmetric with respect to the principal rotation, and both of these are symmetric with respect to inversion, right? A and B is the principal rotation, G and U is inversion. So in all of these, because these are A's and B's, E is always going to be 1 under the E operation. If there were a doubly degenerate one, you would get a 2 here. But A's and B's are not doubly degenerate, they're singly degenerate. So you always get a 1. I just told you what happens with C2, right? C2 is the principal rotational axis. That is the first thing you use to differentiate. A and B are going to be 1 and -1, 1 and -1. Okay. I, that's where the G and the U come in. Symmetric respect to inversion is a 1. Anti-symmetric, that's the U, is a -1. Little tip, there's always going to be an AB type of a group. At the top, that's always all 1s. Look at your character tables, the first irreducible is always going to have a bunch of 1s on it. Okay, and then this guy is a -1 here, a -1, and a 1, which you could do by looking at the product of these two, which should be the same as I. All right, linear functions. So now, where is the z-axis on this thing? You could guess, actually. I'm just going to write them out and I'm going to explain how you would guess. We have a z and an x and a y down there. Notice these are not in parentheses, right? Why not? Why aren't those in parentheses?
Because they transform it.
And how do you know that?
Because there's no, the reason I know is because there's no parentheses there, so they're going to show different.
Yeah, that's right. So because there's no parentheses, it's saying that both x and y functions appear in this irreducible representation. They don't transform together though, and that makes sense because the dimensionality here is 1. When they transform together, the dimensionality will be 2. If x, y, and z all transform together, dimensionality would be 3. So it's like saying they're degenerate, indistinguishable, and they make up one big group when they're in parentheses. This is in a dimensionality of 1, so they cannot be together in parentheses. So up here we've got b squared xy squared minus y squared. These guys are all under AG. And then BG is going to have XC and YZ in it. Okay. So, like I was saying, you can guess where these functions will go. So let's just do a little operation here. You know that basically all of these irreducible representations are orthogonal to each other. And what that means is that we can just think about a z function and not worry about the rest of the stuff. Just think about how a z function transforms according to these operations. Okay, so we're going to look at a z function which has AU symmetry and it has these following characters. So let's do each of these operations for a second. So if we take a z function, we apply the e operation, we're going to get back just a good old z function. And what that means is that the character is going to be equal to 1. Nothing happened, right? Do think back to our matrix multiplication. So we do a 1 times z gives us back a z. That's that 1. Let's do a C2 operation here. Is the C2 operation going to change z? A lot of heads shaking no, but how do you know that? Because
We choose the z-axis to be the principal axis.
that's right. The z-axis is going to be the principal axis, and the principal axis is that rotation. Okay. Put our principal axis along z. So when the principal axis of your function is along the axis, you do the rotation, nothing happens to the function. So you're going to get back z again. What does that mean for the character under C2? 1. It's not going to modify. All right, now let's take a z function and apply the inversion operation. So that z minus z. And that means the character here. Okay, set z to minus z, we gotta have a character of minus 1. And how about our sigma h? Well, where is sigma h? Sigma h is orthogonal to the principal axis. And where is the principal axis? Well, that's the z-axis. Right, so our z function is along the principal axis. We're doing a reflection orthogonal to it. It's going to take plus z to minus z. Okay. So if I do all these operations one by one, and you get out these characters 1, 1, minus 1, minus 1, I can go over to my table here and see 1, 1, minus 1, minus 1, and there's z. And so these guys are just the collection of those things. It tells you how z operates using pretty simple matrix representation. All right. If that's beginning to click for you, how about z squared? What do you think z squared does? Well, we're going to do a z squared orbital in a second, draw it out, think about the shapes and all of that. But a very simple thing you can do is just multiply z by z. Let's do E here. The character under gamma z squared under the E operation is going to be the product of these two. That's 1. In fact, for all of these characters, we're going to do the same thing for C2, I, sigma h, and so on. Take the product of these two. Also equal. These guys are also 1. You know, you're just multiplying minus 1 by minus 1. So what is z squared? Well, all the characters are 1. You can see that all 1s. That's that first row on the character table. And then C2H, that's AG. So you can do sort of simple multiplications using of characters like that to get out useful information. So let's write this guy out here. Yeah.
Can you clarify just what exactly you mean by when you say like a z function or a z squared function? Like what does that look like in that three-dimensional space?
Vector along z.
So what do you mean by when you say like a vector along z squared?
Well, let's take a look at what a z squared function looks like. You can also think about a z function as being a pz orbital. And that's mostly what we're going to use it for. here. Let's just draw up the. How many of you know what DZ squared looks like? Be honest, stick your hand in the air, you know what DZ squared looks like. If you cannot visualize the d orbitals, if you don't know them by name and their orientation, you've got to know that. Okay? Doesn't take that long to figure it out. It's pretty easy, but you've got to go figure that out. The rest of this stuff is just going to be a wash for you if you don't know what the d orbitals look like and where they point to. Okay? DZ squared is sort of the most memorable, especially if you're hungry. Wonderful donuts in the middle. Looks like that. What's the shading look like? The DZ squared donut is shaded. The two lobes are not. Okay, so that's the plus part of the wave. And these are the negative part of the wave. That's DZ squared. It's different than a p orbital. Right? P orbital has plus here and minus here. That's not what's going on. And this lobe points along the z-axis. And this donut sits in the xy plane. So if you sort of look at this vector and swing it around in the xy plane, there's no change in sign. And it's plus up and it's plus down. And so you can say, oh, it's sort of symmetric in all directions. There's no sort of change in sign along the axis. Okay. So if you go about doing these operations now on this function, the E operation does nothing. So it's always going to be 1, 2. For DZ squared orbital, nothing happens. It's a 1. C2, let's take this orbital and spin it 180 degrees. No change in sign, it's a 1. How about a sigma H? Where's sigma H? What plane is that? That's an XY plane, right? This is the principal axis. So sigma H is orthogonal to the principal axis. It slices the donut in half and slices the top lobe and the bottom lobe. But they're plus and plus on both sides of the plane. So there's no change in sign when you do a sigma H. And it's also symmetric with respect to inversion. Because in this part of the donut to that side, or this lobe to that side, there's no change in sign. So DZ squared is great. It's kind of like the s orbital of d orbitals. What the hell does that mean? It means that it's sort of symmetric in all directions. It doesn't change sign very much. So z squared is usually in that top row. All right. How about a p orbital? Just to differentiate. Let's do a P. P transforms just like the X, Y, and Z functions do. Okay, so you can go look at your table and tell me what a P orbital does, but let's do it together. Let's do PZ here. One lobe shaded, the other lobe is not shaded, and this thing is oriented along Z. P orbitals have a nodal plane. Where is that plane? XY, right? An inversion operation. inversion operation changes the sign of the function. So is a p orbital Garada or ungarada in this symmetry group? It's ungarada, changes sign when you apply an inversion. That is ungarada. So you know, ignore these for a second. Better have a, it's going to be part of these two groups. Now what makes it A or B?
CT2.
Principal axis of rotation and how it changes, whether or not it changes sign. PC is oriented along the principal axis. You do your 180 degree rotation. There's no change in sign. That means it's an A. So PC is AU. Okay. That's how you can use these things. Pretty convenient, yeah.
I'm just wondering, as you go to higher principal quantum number and you add nodes into the orbitals, will that ever change the symmetry?
No. No. There are spherical radial nodes, so no. Okay. Let's do some d orbitals here. First of all, you might say, all right, so quadratic d orbitals are quadratic functions, and all of the d orbitals here are in the G groups. D orbitals are always symmetric with respect to recursion. The dz squared that we showed up there is like that. The two lobes are the same sign on opposite sides of the d orbital, right? The same is true for the other ones also. Let's take a look at so the convention that I like is not necessarily the same as the way you're applying everywhere else. Okay? I promise you it's simpler. So there are d orbitals that are aligned with the x, y, and z axis. There's two of them. We've already talked about one. dz squared points along the z axis. There's a d orbital that points along x and y. And that one is x squared minus y squared. So all the ones that have the square symbol associated with them are along the axis. The other ones are between the axes. X, Y, X, Z, and Y, Z. They're all kind of the same. They're just oriented differently. Their lobes are between the axes and they have nodes where the axes are. If you use that organization, life is easy. Sometimes people say X, Y is on the axis. We're not going to do that, okay? If you do that, we'll be frustrated and try not to mark you wrong. But what I'm going to teach and, you know, the answer keys and all of that stuff, this XY orbital, the lobes point between the axes and the nodes fall on the axis. We'll draw that out in just a second.
Does that mean that both the xy and the x squared minus y squared fall in that xy plane?
Correct.
And why is that the only plane that gets two orbitals falling? Why don't any others?
Well, the dz squared is also pointing along the same directions as xz and yz. So it's not the case, I guess, is what I would say. All right, so xy points between the axes, and I'm going to try and draw carefully here. Okay, so this lobe, just coming out at you, is in between this axis and this axis. Okay, This lobe here is between these two axes. This lobe is between this one and this one. This lobe is between this one and this one. And there are two nodal planes here, this guy and this guy. And they are along the z direction, and they are coincident with the x and the y axes. All right, so let's do inversion operation. What's the inversion operation we could do with that orbital? Nothing. Because the lobes have the same sign across the center of the coordinate system. Okay, the inversion does nothing. How about sigma h? Nothing. Slice this guy in half, right? This is in the xy plane. So slice it in half. A bagel or something like that. And the top half and the bottom half are identical. Okay. Sigma h does nothing. And that tells you since I does nothing and sigma h does nothing, C2. Product of C2 and sigma h is I. So this guy is AG. And characters here. There it is, Z squared. All going to be ones. All right, let's do. Let's do an XZ or let's do a YZ here. Let's start. Drawing the ZY plane. I'm interested in the DYZ orbital. The DYZ orbital sits in the YZ plane. Now, where are the lobes in this YZ orbital? Are they on the axes? Between the axes? They're between, right? Only z squared and x squared minus y squared. The squared ones, those have lobes that point right along the axes. The other three, the lobes point between the axes, and there's three different possibilities. YZ is one. Just like that. There are nodes, two nodes. S orbitals have no nodes, p orbitals have one node, d orbitals have two nodes, f orbitals have three nodes. I don't know what the next symbol is, but it has four nodes. So these things are Garada, they're symmetric to spectral inversion. Lobes point to the axis, and we can draw our other one in here as well. All right, so let's do some characters here. The E operation does nothing, always going to be one. Let's do C2. Let's C2. -1. How many people like -1? How many people like +1? How many people don't like answering questions? That's sad. What's that?
It's negative.
It's negative.
Rotating sign.
Right, because you're going to rotate this thing, this lobe's going here, while we went from plus to minus. So that's anti-symmetric, it changes sign. Do that. Sigma h. Where is sigma h? Well, this axis is along z. Sigma h is the xy plane. What happens to this one? Plus to minus, anti-symmetric with respect to sigma h. How about with respect to inversion? Well, you can say, well, the orbitals are symmetric with respect to inversion. That must be true. So it's errata, therefore it's 1. Or you can say, hey, if I multiply the characters of C2 and sigma H by one another, I'll get +1. Or you could just look at the thing and say, oh, well, plus minus. And where is that? That's BG. Okay, so cool. This is great. These tables, pretty easy to use. You can look at a shape. We're going to be looking at a lot of d orbitals and estimating what their symmetries are. Look at the shape of the thing. You can determine the symmetry of the character.
Last class, we had Rx, Ry, and Rz as well. How would you visualize those?
I'm not entirely sure. I believe I would think about like left-hand rule or right-hand rule and left-hand rule, and think about how those functions would be transformed. I think that that's the right way, but I've never really done it. Okay. All right. So there's all this matrix multiplication stuff, mathematical representations, building up these character tables and everything. There's all this sort of supporting math, but it's pretty easy to just do these kinds of mental transformations and know symmetry, and also to look at these tables and sort of think about, they're just sort of really handy references in thinking about the symmetry of stuff. And that makes life very nice and easy, as we will see. All right, so now we're going to jump into molecular orbital diagrams, my favorite topic. And something that I really want you guys to be good at. Really important. You take an organic chemistry class, or you argue about an organic chemistry mechanism. People get up there and they draw long pairs, push the electrons around, and they say, well, the LUMO is over here. This is the empty orbital, and it gets attacked. All of that stuff presumes some knowledge of where the electrons are, shape of the molecule, which electrons are most reactive, which sites are most acidic. You can't think about that stuff unless you can do an analysis of electronic structure. And for transition metals, that's kind of harder than it is for organic molecules. There's more d electrons to worry about. They have funnier shapes. So you need to be able to think about the bonding. And it's not quite as straightforward. So we're going to learn how to think about bonding using the LCAO approach. Bonding in transition metal complexes is very delocalized. It's more delocalized than I am going to give it credit for in the lecture. And you need to learn to think about orbitals composed of many atomic orbitals combined together in order to talk about that type of thing. All right. So we've already talked about the LCAO approach. What is the LCAO approach? LCAO stands for linear combination of atomic orbitals. You can make a molecular orbital by combining atomic orbitals in a linear combination. When we did resonance structures, we said, this is a good description, this is a bad description. That's like the coefficient in front of the linear combination term. Right? Big coefficient means big participation. So you can do that by making molecular orbitals. So let's take a look. Simplest molecule, H2 radical cation. We're going to have two different hydrogen nuclei, A and B here. They're going to be separated by some distance. Because it's an H2 radical cation, we have one electron to worry about here. That's the separation between atom A and that electron, atom B and that electron, and this is kind of a solvable problem. And so people write out the wave function for this sort of a molecule in the following way. They say, well, we're going to get a sigma bond here. Two s orbitals. And it's going to be the product of some coefficient for atom A and its component orbital psi A and some component from atom B also modulated by its coefficient. So that is the bonding combination. There's also an anti-bonding combination. The anti-bonding combination is just the out-of-phase combination of the same orbitals. That's how you get bonding and anti-bonding. In phase and out of phase. These are the destructive and constructive interferences of two s orbital functions. Two s waves. And people make these orbital interaction diagrams where you take one SA and one SB. This is on the energy axis now. With energy, the s orbitals, they combine. Get some bonding interaction. This is the sigma bond, and this is the anti-bond, and there's some splitting here. This energy splitting is, people say the homo-lumo gap. And if we have one electron here and one electron there, down here we have a pair of electrons. There's your HOMO. There's your LUMO. So the other way people represent this stuff is by actually writing out the wave function. So let's write out the orbital representation of this wave function. You have two s orbitals that combine in an antisymmetric way or in a destructive way. They have opposite signs, and between them there's a node. This is the anti-bonding orbital. The destructive interference of those two. When the two waves add together in a constructive fashion, you get one new big wave without a node, and that's the bonding orbital. Okay. So you could write this thing out if you wanted to. Psi 2, which is the second highest wave function, could be 1SA minus 1SB, and psi 1 is bonding orbital, 1SA plus 1S. Okay, so that's all pretty familiar, I hope. Let's do something a little more fun. Let's look at V2, vanadium, divanadium. Now we're gonna make an orbital interaction diagram. We've got some more interesting things to combine. Let's take 5 d orbitals. These are 3 d orbitals on vanadium A. We're going to combine them with 5 3d orbitals. How do they combine? Well, you're going to get bonding and anti-bonding levels again. There's actually a couple of different types. You don't have simple degeneracies. Okay, you end up with a d sigma, a d pi, a d delta, and the corresponding antibonding. So what do those guys look like? Turns out this sigma bond is made, we're going to pick, hence you could sort of choose different axis systems if you wanted to. To make this easy on ourselves, we're going to choose the z-axis on the internuclear axis. This molecule V2 is d infinity H, cylindrical linear molecule. It doesn't point in either direction. That's a d infinity H. So we're going to put that z along that internuclear axis, and that makes this d sigma orbital 2 orbitals. That have the same sign pointing at each other. Z squared plus z squared. Let's do some pi bonding orbitals here. What do the pi bonding orbitals look like? When you have 2 d orbitals, there's 2 possibilities actually. Easier one to see . Tired looking. There's pi bond between 2 d orbitals. Notice how the lobes here that are kind of pointing at each other have the same signs. There's another one that looks a little bit like this. It's the same type of orbital, it's just instead of in the plane of the board, it's sort of laying down. Same situation. So we've got 2 nodes, sorry, 2 lobes pointing at each other. You know, if I just forget about the other side, it kind of looks like 2 p orbitals that make a pi bond in that or something like that. That's a pi bond for you. Let's look at the delta. An awkward pairing. And They're not really pointing at each other. They're just sort of like cozying up side by side. But in this region, you notice they have the same sign. In this region, they got the same sign. And in the back, that's a bonding orbital. And this guy here. That's another view. Now, we get familiar with those with time. Couple of things to know, okay? When you have a sigma bond, there are no nodes along the internuclear axis. A pi bond, there is one, right? There's a node right here. Both sides of that molecular orbital share the same nodal plane, and that nodal plane contains the atoms. These guys have two shared nodal planes. This one here, this molecular orbital, the plane of the board is a nodal plane. And there's also that nodal. And both of those nodal planes contain the nuclei. That's what makes it a delta bond. That's the definition. Okay. If there is a node containing the atoms, it's a pi bond. If there's two nodes containing the atoms, it's a delta bond. The sigma bond has no nodes.
Does that mean the only orbital that can do the sigma bond is Z squared or out of the G?
Yes. Well, it's not the only orbital that can do sigma bonds. You can take the lobes of 2D orbitals and point them directly at one another. And there's no node containing both of the nuclei. And now it's, you need a node along the internuclear axis to make it a pi bond. You need two nodal planes along the internuclear axis to make it a delta. You can take a d orbital, which has got all these funky nodes going all over the place, but if the lobes are directed at each other, and directed meaning along the internuclear axis without a node along that internuclear axis, then all right.
Sorry.
It's okay. That's right. So without a node along the internuclear axis, it's sigma bond. Okay.
Both of the nuclei have to be in the same node, right? Even though there's a node at the nucleus, because it doesn't contain both of them, it would still be.
Yeah. So like if you have two p orbitals pointing directly at one another, their lobes butting heads, that's a sigma bond.
The splitting in energy of the different MOs just caused by like the geometry, how you combine.
That's a way to say it. I would also say the sort of simpler, more qualitative picture that sticks in my mind is that when the orbitals are pointing right at one another, you get a much stronger interaction, and that leads to a bigger splitting in energy. Think about like the steepness of the wave function. This is the bonding combination. But if you have an anti-bonding combination of these two, when you travel along that internuclear axis, you've got to go through zero. And there's a steep function here. It's because they're not really directed toward one another, but they're just sort of like cozying up next to each other. The strength of the interaction is weaker. And that is represented in this diagram. Right? The magnitude of the splitting is the greatest for sigma. It's the lowest for delta. And that is a very good rule of thumb. It is not always correct, but almost always correct. And you just assume it. And, if you're going to propose something else, you're going to have a big, long discussion with people that really care about this stuff. Yeah.
What's the orientation of the like combination of atomic orbitals that leads to the anti-bonding sigma orbital, like to that,
It's the same orbitals. It's the same orbitals, they just have different sign.
okay,
So take the one on the right and make it negative, keep this one positive, and then you get something that's the same place.
it's not like the round part, like, looking towards that low, that like, okay.
No, it's just a change in sign. It's the constructive and destructive interference of two waves. Right? Bottom one is the constructive, the top one is the destructive. Okay, so you get better overlap for sigma. The 4 delta orbital is the weakest bonding interaction. Sigma is in charge. Sigma orbital is most, sigma bonding is most important, then pi and delta.
Just to double check, is the DC squared orbital degenerate in all the other p orbitals?
Depends upon the symmetry of the compounds.
It depends. Because like, I don't know, it just looks so different, like the shape is so different.
Yeah.
I would expect that it would have like different values.
dz squared and dx squared minus y squared are often degenerate. In systems where x and z and y all transform together, they're equivalent. So for instance, octahedral with EG and T2G, dz squared and x squared minus y squared are part of EG. They're degenerate, even though they look different.
So sometimes if you want it to be like super precise in the MO diagram, the atomic orbitals would be like slightly separated.
Well, what you're going to find is that these diagrams are teaching tools. We can make them look kind of however we want as long as we obey some principles. What I mean when I'm saying this is I started with the 3 d orbitals like this, right? This is my basis set. That's what a basis set is, kind of like your starting deck of cards that you're playing with. I didn't include the 4s. I didn't include the 4p. I could have hybridized and started from hybrid orbitals if I wanted to. So you can make these diagrams a lot of different ways to illustrate a point. And for our purposes, this way shows you how the d orbitals split in this energetic arrangement. We show the differences between sigma, pi, and delta. The small perturbations you're talking about. When you're referring to the starting state, you can kind of pick your own starting state, as we'll see. All right, so sigma is better than pi than delta. We're going to hear that again and again and again. So let's do some other situations here. Sure. Let's do the CH. Now we're going to take a carbon three carbon 2p orbitals. And I'm going to interact them with one hydrogen, one s. I started them at different energies this time. Why is that? Well, the ionization energy of the atom, P and hydrogen 1s, they're not the same. So now when we make a bond, something like that. 3p orbitals, only one of them is going to point at the hydrogen, and the other two do not. So this guy down here is the sigma, CH. This is the sigma star, CH. And since this molecule is C infinity V, our z-axis is going to be oriented along the CH bond. The PZ orbital, which is along that axis, is going to be the one that points at the hydrogen. And so the PZ orbitals used to make the sigma bond, PX and PY, do they transform together or are they distinguishable? They're distinguishable? No. What I mean when I say that is if I said, all right, let's say I had a model kit, just a CH bond here. I said, okay, this direction is the X direction, all right? And there's a PZ, let's say it had two p orbitals on it. I said, this one's the PX, and I threw it to you and I said, which one's the PX? You couldn't tell me. Unless you somehow saw it flipping in space. But the X and the Y directions are degenerate. They're the same direction. It's just a naming system, which is X and Y. They're indistinguishable from each other. Okay, so PX and PY are going to transform together in this symmetry. All right, so these guys, PX and PY, they are non-bonding. Now, how do I know they're non-bonding? Well, let's draw one of them out. This is our z-axis, right? That way. We got our hydrogen over here. Is there a bond there? Remember that there's a node. Right? These guys have totally different nodal structure. They cannot make a bond. They are orthogonal. This S orbital falls right on the node. Those two guys do not get along. They are orthogonal. So this is not a bonding interaction. It's not a non-bonding interaction either. Sorry, it's not an anti-bonding interaction either in this boat. Right? An anti-bonding interaction is still an interaction. It's an destructive interference. These two things are not going to interfere with each other. They have totally different nodal structure. They are non-bonding, and both PX and PY are like that. They have a node that runs along the internuclear axis that the s orbitals don't share. And it's true for this guy. Non-bonding. Now, if I draw out bonding and anti-bonding orbitals here, what are they going to look like? Well, another rule of thumb that's very important to consider is that these diagrams, you can think about them as this carbon is perturbing this hydrogen's energy. And this is the perturbation. This orbital down here is going to look a lot like this hydrogen 1s orbital because they're close in energy. These two guys are close in energy. That's going to make this sigma star orbital look a lot like a carbon 2p orbital. So the coefficients that you use in your linear combination depend upon the energy separation. There is your sigma star. It has more carbon character than hydrogen character. There is your sigma. It has more hydrogen character than carbon character. Why is that? Because of the proximity and energy. Okay. This guy is close to this guy, closer to it than this one. the wave functions then tend to look like the parentage. Okay? All right, so when you put your atomic orbitals on your diagram, they need to be ordered based on the energy of your parentage. You can pick lots of different orbitals with which to make a diagram. We're going to talk about atomic orbitals. Atomic orbital energies. You can look up in a table if you want. Carbon is above hydrogen. Oh yes. Important reference point. You look up the ionization energies, they are all referenced to the vacuum level. Where's the vacuum level?
Looking abstract values. I won't say it's infinity, but an abstraction that is not 405.
Yeah, it's, you know, it's an arbitrary energy, but it's not a fictitious one. It's the real energy of an electron, unperturbed and at rest in empty space. Right? Where is that on this diagram? If I said I have a hydrogen atom in a vacuum, would it take energy to pull the electron off of that hydrogen atom? Yeah. That, the difference in energy between here and the vacuum level, that's the amount of energy. So the electrons fall down to land in this level relative to the vacuum. Vacuum is way up here. If the vacuum level were below these things, then any electrons in CH would get spit out into space. Right? So the vacuum's way up here. Interesting fun fact. Diamond, we're going to eventually get to solids. Diamond has an orbital diagram also. And the LUMO in diamond is above vacuum. Diamond can actually spit electrons out. A little electron gun. All right.
The LUMO is unoccupied.
Sorry?
But isn't the LUMO unoccupied? How would it?
The LUMO is unoccupied unless you throw an electron into it. So if I have a chunk of diamond and I wire it up, and I force electrons into it, you know, with a big motor, they'll come streaming out of that diamond at the energy of the LUMO level.
Can you excite it with light as well?
Yes. You excite diamond with light and it will arc. It will spit electrons out at you. And this happens when you walk around outside with a diamond ring on.
What energy of light do you need? Is it UV?
UV, 5.5 electron volts. That'll give you a heck of a sunburn. All right. Okay, so we've done a couple of these things. I'm going to repeat them next time, but since we just have over 2 minutes, I'm going to mention one more. When you make an orbital diagram, we're starting with 3 and 1 component orbitals. You don't get to just delete one or add one later. Once you start with 4, you better end up with 4 in the product. You started with 5 and 5, you better get 10 in the middle. Okay? Orbitals must be conserved. The magnitude of the energy splitting, it's all about overlap. When the orbitals are pointing right at each other, you get big splittings. What defines a pi bond? How do you define a pi bond simply? Well, p orbital has a nodal plane, but it can make a sigma bond, so that's not enough.
No free rotation.
No,
Free rotation.
That's a property of the molecules, like atoms. What I want to know, that's what you're saying is a smart thing and correct, but that's not how to define a pi bond. I define a pi bond in terms of nodal structure. William?
Nodal plane along its internuclear axis.
Yeah, if there's a plane, a nodal plane along the nuclear axis, the bond between the two atoms, if there's a plane that runs along that axis, it's a pi bond. You have two p orbitals side by side, like you do in ethylene. The carbons are in the middle of them. That's the bond between them. And there's a node running along that bond. That's what makes it a pi bond. If you have a node here and you have a node here along that internuclear axis, you have a delta bond. Sigma, there's no node along the internuclear axis. It's just two things pointing at each other. No nodes there. It's only when there's a plus on one side and a minus on the other and a node that you get a pi bond. Plus, plus, minus, minus is a delta bond, right? Nodes along the internuclear axis. All right. The only other thing is this energy difference stuff. This molecular orbital looks more like this atomic orbital than this one, because they're closer in energy. And the last principle that is probably worth paying attention to is that orbitals that have about the same energy tend to make stronger interactions. If you have two orbitals that have very different energies, they don't interact very well. Okay? So the closer and closer they get to each other in energy, the stronger the interaction. And that rule is not as solid, but it is relevant. Okay, so next time we're going to actually use group theory to put some of these things together. And that's when life gets a little complicated. Come on. Thanks so much. We'll see you guys next week.